always seems like complete nonsense to people when they first start studying relativity. Just like we usually want to start kinematics problems at x equals 0 to make our lives easy, we're going to start this problem with two identical twin babies, so their ages are 0. What we usually do in this problem is to say we're going to leave one baby on Earth and put another one on a rocket. We can just as easily, instead of on the Earth, we can leave the baby stuck in a spaceship here near the Earth. So we can also imagine like a conveyor belt or a subway, a train of rockets, all heading from Earth to this nearby star. And we just sort of throw one of the twin babies on this high-speed train and let the train take them to the star. You can actually do the math involving accelerations with relativity. It's a common misconception that special relativity, only deals with unaccelerated motion, and that's not right, but it's easier to just avoid that. So we're just going to say the acceleration is basically instantaneous. We throw the baby on this high-speed train, and then we want to know if the star is 10 light years away, how long will it take the train to get there? We know it would take light 10 years to get there because that's what a light year means. The rocket has to take longer than 10 years because it has to go slower than c. We can't have anything with mass going the speed of light. So we come up with this number 0.994987 c. Just like people who work with aircraft, especially fast ones, might use Mach number as shorthand for a fraction of the speed of sound, we can use this thing beta, which is our velocity divided by c, to represent that fraction of the speed of light. So we would say beta in this case is 0.994987. We're never going to get beta greater than 1, though. You can have Mach numbers greater than 1, but you can't do that for beta. The reason I picked this number is it gives us a gamma of 10. So the twin that stays home would say the clock on the rocket is moving at 1/10 its proper speed. It's gaining 2.4 hours a day instead of 24 hours a day. So the twin that stays home says, okay, according to me, it's going to take 10 divided by beta years for the rocket to reach the star. So that's just over 10 years, because remember, we're traveling very close to the speed of light. The twin that stays at home also says, because the clock is so slow on this moving train, the traveling twin is going to only age 1/10 of that. So it'll take 10.05 years to get there. He's going to age 10.05 divided by gamma, about a year. Now, what does the traveling twin say? He says the star is racing towards him at high speed. And the Earth and the star are moving at the same speed, so the traveling twin sees both the Earth and the star racing to the left at crazy high speed. Because it's moving towards him at high speed, he says that distance is not 10 light years anymore. He said it's 10 over gamma, or 1 light year. So this star is only 1 light year away, and it's headed for him at almost the speed of light. So he says in 1.005 years, that star will go flashing by my window. Now, since the twin on the rocket thinks the twin on the Earth is really doing the moving, he says the Earth clocks are going to be slow by a factor of gamma. So he says the Earth twin only ages about 1/10 of a year. On the trip back, easiest thing to do is pretend there's another rocket subway headed that way, same speed, and the twin just jumps from one to the other. Forget the fact this would turn them to mush. We're just going to pretend they can survive. The twin jumps from the outbound rocket train to the inbound rocket train. We assume an instantaneous turnaround. So back on Earth, that twin says, all right, this trip is going to take 20 light years divided by beta, 20.1 years. But he also says the rocket twin will only have aged 2 years in that time. Now, the guy on the rocket says the total trip will be 2 years for him. The total, these things moving back and forth. That'll only be 2 years for him, but he says he's aging faster, and the Earth twin will only be 0.2 years older. So they both agree that the traveling twin is 2 years and some change older, but they disagree about whether the twin that stayed home is 2/10 of a year older or 20 years older. Now, the apparent paradox is we've said that if the two inertial observers are in relative motion, they can each claim they're not moving. But there's no way both twins can be correct. When the traveling twin gets home, his brother is either going to be a few months older than, a baby that's a few months old, or he's going to be 20 years old. The way we figure out who's right, it turns out it's the twin that stayed home on Earth, and it's not because of Earth. The reason he's right is we said we had to have an inertial observer, an unaccelerated observer. And the twin who got on the rocket is the one who had these extreme acceleration events, one when he left for Earth, then another one when he came back. So we can't trust his elapsed time estimates. This is kind of like the way in early physics 1 when you looked at a block on an inclined plane and you saw you could do it with vertical and horizontal x and y, or you could tilt them a little bit so that your x prime is along the plane and y prime is perpendicular to the plane. In this case, either way, you'll get the right answer if you do the right thing. If you use the coordinate system on the left here, you might say delta x is 4, delta y is -3. If you use the prime coordinates, you'd say there is no delta y prime change, it doesn't go up or down. Delta x prime is 5. The components are different, but the lengths agree. So if I do 4 squared plus -3 squared and take the square root, I get 5. If I do 5 squared plus 0 squared and take the square root, I get 5. The physical thing, we agree no matter what. Now, what we can't do, we can't say, well, all right, let's take delta x and delta y prime and combine those. If we do that, we'll get garbage, and that's what this twin is doing when he predicts the Earth twin is only 0.2 years older.